Hello and welcome to section 5.1, Eigenvectors and Eigenvalues. So we'll talk about what eigenvectors and eigenvalues are and learn how to determine whether a given value or vector is such. And then we'll also find the basis for something called the eigenspace of a matrix and talk about how to find eigenvalues for a triangular matrix. So to start with, let's say we have a matrix A and a vector V, and the first question asks us to draw a picture of V and AV in the coordinate plane. So let's go ahead and compute AV, and when you do that multiplication, you get 20, 10. And so here, our vector V is 4, 2, and then our vector AV is 20, 10. And so what you should notice happens here is AV is actually exactly 5 times vector V. And our next question asks, is this, so basically what AV does is it multiplies V by 5. And then the next question is, well, does this happen in general? Does multiplication by this matrix A always just multiply by 5? So let's look at another vector. Let's just look at something simple like 1, 1. When we do that multiplication, we get 5 on top, but then we get 2 plus 1, which is 3 on bottom. So our multiplication by our matrix A doesn't always just stretch our vector. So V was sort of special in some way. And that's kind of the idea behind eigenvalues and eigenvectors. So an eigenvector is a special vector such that when you multiply it by a matrix A, you get just a multiple, which we'll often use lambda to refer to that multiple. And that multiple, by the way, is called an eigenvalue. One subtlety that's important to remember is eigenvectors cannot be 0, but eigenvalues can. So eigenvalues can be 0, but eigenvectors cannot be the 0 vector. And we'll talk about why not, but the main idea is that if you multiply the 0 vector by a matrix, you always just get back the 0 vector, so it's essentially just kind of trivial. And then so if you're given an eigenvalue, so basically the key equation that you want to think about is AX equals lambda x, and anything satisfying that is an eigenvector corresponding to lambda. So this x here, any solution here is an eigenvector corresponding to lambda. Okay, so let's test this. So we multiply -3, 1, -3, 8 by 1, 4 just to see if 1, 4 is in fact an eigenvector. And so when we do that multiplication, we get -3 plus 4 and -3 plus 32. And so that gives us 1 and 29, which is not a multiple of 1, 4. So that's not equal to lambda times 1, 4, no matter what we choose for our lambda. So no, 1, 4 is not an eigenvector for this particular matrix. And now the next question asks, is our vector 1, -2, 2 an eigenvector for this given matrix? And if yes, find the eigenvalue, which means tell me what multiple you need. Okay, so kind of like up here, this eigenvalue is 5. So 5 is the eigenvalue for the eigenvector V. Okay, so now sometimes we might be given information, like here, we know that lambda equals 2, or we're given that lambda equals 2 is an eigenvalue for this matrix, and we want to find the corresponding eigenvectors. And so what this is saying is that this matrix 3, 2, 3, 8 times some vector x equals just 2 times that vector x. And so we want to somehow, to find the eigenvectors, we want to solve this for x. But right now that's a little tricky. We've got x showing up twice. So we might want to start by just subtracting the x on the right-hand side so that we have all of our x values on the same side. But the only issue here is that we want to be able to factor out that x, but we have a matrix and a number, right? So we can't just factor out. It doesn't make sense to write 3, 2, 3, 8 minus 2 times x. That doesn't make any sense. That's bizarre, right? But we need a 2 by 2 matrix here. But 2 is just like 2 times the identity matrix, because in matrix world, the identity matrix really corresponds to not changing anything. Okay, so, and by the way, let's just, in case that seems a little wacky to you, let's think about what happens to a vector when we multiply it by 2 times the identity matrix. If you do that multiplication out, you really do get 2 times x1, 2 times x2, which is the same thing as just multiplying that vector by 2. So that's an aside, just to make sure you understand that I'm not like making something up by just sticking that identity in there. It's kind of neat though. It's really because 2 times x equals 2 times the identity times x, and so that therefore becomes 2 times the identity times x by associativity. That's also a little bit of an aside, so we'll keep that there. Okay. So now we have something we can work with. So we have 3, 2, 3, 8 minus 2, 0, 0, 2 times our x vector equals 0. And so this tells us that we have 1, 2, 3, 6 times x equals 0. And now we just need to find, we still need to solve for x, so we need to row reduce. And so if we take 1, 2, 3, 6, and we apply row 3 minus 3, row 1, we get 1, 2, 0, 0. And now we know how to solve this, right? We have x1 equals negative 2, x2. x2 is free. And so our eigenvectors are all of the form negative 2, 1 times something. So another way to write that is the span of this one vector. And so this is all possible eigenvectors for lambda equals 2. Oops, eigenvectors for lambda equals 2. Okay. So our next quiz question asks us kind of a similar type of deal, where you want to test whether 4 is an eigenvalue of this 3 by 3 matrix. And the setup is essentially going to be the same as what we had before. We have this matrix 3, 0, negative 1, 2, 3, 1, negative 3, 4, 5. Right, our equation is this times x minus, well, really, we started out with that has to equal 4x, but then we can, remember, we can subtract this, and then that 4x is actually 4 times the identity times x. And again, it's really that identity is multiplied by that x vector to not change it, which means we can multiply it by our for I. And so this boils down to solving the system that looks like this. So to solve this quiz problem, you need to do that subtraction, and see if it has any non-trivial solutions. And so if it does have any non-trivial solutions, give you an eigenvector. Okay. So let's take this and make it more general. So if we're given, recall we have this equation ax equals lambda x, and we really want to make a homogeneous equation, so we can do what we've been doing and rewrite this as ax minus lambda x equals 0, or ax minus lambda times the identity x equals 0, and then let's pull that identity in with the lambda rather than with the x. And so now we can use the distributive property of matrix multiplication to get a minus lambda I x equals 0. And so remember that the null space of a matrix B is the set of all solutions to B times x equals 0. So here then we're looking for, if we want to find all the eigenvectors for A corresponding to an eigenvalue lambda, well, that is equal to the null space of A minus lambda I. So even though we're doing something new, we know how to compute the null space. So the way we're doing it and the computations that we're doing it are not brand new for us. Okay, so we can use what we're used to doing to find the null space, and in fact the null space is often referred to as the eigenspace. So finding all the eigenvectors corresponding to lambda is equal to finding what's called the eigenspace corresponding to lambda. So here, and it is a subspace, so let's do that for this particular situation. So we have 4, 0, negative 1, 3, 0, 3, 2, negative 2, 5, and then we're subtracting out 3 times the identity matrix. And so what we're left with is 1, 0, negative 1, 3, 3, 3, oh, 3, 3, oh yeah, 3, minus 3, 3, and 2, minus 2, 2. And so what we end up with is we can now okay, so now we have our A minus lambda I. So this right here, sorry about the beeps, is A minus lambda I. And so we want to find the null space of that, and we want to find a basis for it. We know how to do that. We're going to row reduce. So let's row reduce here, and we can divide, let's take row 2 divided by 3. And you'll notice that row 2 is the same as row 3. I'm going to save us some time and just write it like this. And so now, let's see, we need to then take row 2 minus row 1. So I did some stuff to row 3. Keep that written down. Okay. And so we get 0 minus 1, and then 1 minus negative 1 is, I believe, a 2. And finally, we should multiply row 2 by negative 1 to get rid of that negative sign. So 0, 1, negative 2, 0, 0, 0. And so we have our top line is x1 equals, I'm going to go ahead and solve for x1. x1 equals x3, x2 equals 2x3. If you're not following this, go back and make sure you go back about how to find the parametric vector equation for a solution. And so we have all multiples of 1, 2, 1. And so in fact then a basis for this eigenspace, which I sometimes write as I of a comma lambda, is just the vector 1, 2, 1. So notice here I'm not writing span because a basis is the set of all vectors that are in the span of our sorry, the eigenspace is the span of all the vectors in a basis. And so this is abbreviation for eigenspace of A corresponding to lambda. I don't think your book actually uses that specific abbreviation, so just so you know, it's kind of you might not see it there, but you might see it in other places. Okay, so the eigenvalues of a triangular matrix are actually just the values on the main diagonal, and you can kind of see that by if you subtract one of those out. Like if you subtract the identity from this matrix, I'm just going to write out what we get. You will end up with 3, 3, negative 2. And you see that 0 showing up there. It's going to make one of those entries go away and convert that column into corresponding to a free variable. And that's what gives it that non-trivial solution. So I've asked you to write down what the eigenvalues of this particular matrix are. Okay, so what does it mean if a matrix has eigenvalue 0? Well, if we have A times AX equals 0x, so remember, eigenvalues can be 0, eigenvectors cannot. Well, that means that just AX equals 0 has a non-trivial solution. It has to be non-trivial because the vector has to be non-zero. The eigenvector has to be non-zero. And so that actually means that the columns of A are linearly dependent. Right? If we have a non-trivial solution, that means there's a free variable, so those columns are linearly dependent. So by the invertible matrix theorem, part E, A is not invertible. So now we have another thing that tells us about invertibility. If we have an eigenvalue of 0, then our matrix is not invertible. Okay, and the last thing I wanted to talk about today is about eigenvectors coming from distinct eigenvalues. So if you have different eigenvalues, their corresponding eigenvectors must be linearly independent. And so here's an example for us. We have a matrix A, and it actually has 3 distinct eigenvalues. And it has eigenvector U is one of the eigenvectors corresponding to eigenvalue lambda equals 2. And then we also have V, which corresponds to lambda equals 3. And so because those correspond to different eigenspaces, then they must be linearly independent. So they come from eigenspaces for different eigenvalues. And we'll stop there.